Hey friends, I'm Carmen and I'm one of the educators at CuriOdyssey. Maybe you didn't know this about me, but I love snacks. And I get the feeling that some of you might love snacks too. Well, the last time I wanted a snack, I decided to do a little bit of science. So I did a little bit of kitchen chemistry and I videoed along with the experiments I tried. First, I wanted to know if it would be possible to make a delicious dessert using my microwave. And after I made that dessert, I was so curious about the chemistry that happened inside of the little cake that I made. So I went on and I kept experimenting with some of the ingredients to see if I could notice more about the chemical reactions inside of a baked dessert. If that sounds like a cool activity for you, or if maybe you're just a little bit hungry and want to learn how to make a fun snack, check out my little video journal that I have coming up next. I hope you'll join me. Hey at home science world. So I've been working on a bunch of plant experiments, but I kind of want some food now. I thought that I could do some science to make a snack that I don't have to wait for it to grow. I might have to wait for it to cook, but I don't have to wait quite as long as it will take to grow a fruit or a vegetable or some of the other things I've been experimenting with. So I found this website over here. I'll show it to you up close. Okay, this is what I found. I found this website called Gemma's Bigger, Bolder Baking that claims you can make delicious food in a mug just using some ingredients at home and your microwave. It looks too good to be true, so I want to test this out. Over here in the ingredients list, it looks like I already have all of these things at home and that it should be pretty easy to make. I'll take a look through my pantry and my fridge to make sure I have all of this stuff. I'm a little bit nervous about how this is going to turn out, but we'll see and we'll give it a taste test. Alright, here are all of the ingredients and measuring tools that I got out that we'll be using for this little kitchen chemistry project, the microwave mug cake. And last but not least, the mug. I know my friend educator Rasheen will love this little shout out to her favorite animal. So I think we're all set and ready to start mixing some ingredients together. Alright, moment of truth. Will there be a scary blob of dough? Or will there be a cake? Oh hey! It's got a little bit of a weird blob there in the middle, but yeah, definitely. Looks like something interesting happened. Let's do some science before I take a taste and see what happens. Okay friends, so here I am with the mug cake. I think it's a little bit hot right now, so I'm gonna let it cool down before I try anything else with it, but it smells really good. It smells like the cinnamon that I sprinkled in there, and I was looking inside just while I let it cool. I don't want to touch it with my hands yet, but it has some interesting bubbles and textures, so it looks like it did cook in the microwave. I'm excited to open it up and see what it looks like inside. Alright, it's been a few minutes and I think we're ready to take a look inside of our cake. I have this little spatula that I think will help me to get the cake out of the mug. So let's go ahead and try that. Alright, and yes, this was meant to be eaten just straight out of the mug, but the hunger for science and curiosity speaks louder than the stomach. But if I were in a hurry, I'd probably just top this with jelly and eat it out of the mug. Since we're doing science though, let's take a look at what we have. What do you notice about the texture of this cake? One thing that I see all around the edges are these different shaped bubbles. And right over here, like this really big bubble that looks like it circled the whole edge. So these aren't places where like I ripped the edge of the cake. I'll do a test just to make sure, but I think these were gas bubbles that formed while the cake was baking, and as the batter solidified, those bubbles were kind of frozen in place. Let's take a look in the middle just to make sure that wasn't just me scraping it too hard on the edge. If we see bubbles here on the inside, we'll know they weren't just imperfections on the outside that we're seeing in this interesting texture. Ready? Alright, here it is. In the middle of the cake, it looks like it also has these varied shapes of bubbles. Huh, that's really neat. I'm going to show you the other side too, and then we'll get this dressed up and plated to eat. So it looks like this side also has some of those interesting bubble patterns. So I know that I've heard about baking powder and how it helps cakes to rise and have like this spongy, fluffy texture, but I'm not quite sure about the chemistry behind it. So that's still something I'm wondering about and might do an experiment next. So I'll get this cake decorated with some jelly like it's supposed to have, and we'll do a little taste test. Okay, taste test. It's actually pretty good. I am definitely impressed by how this tastes. It's moist, it's pretty fluffy, and it's not too sweet. So having the jelly on top is perfect. Snack success. Well, what did you think about the microwave cake experiment? It turned out as just an idea when I wanted a snack, but it really turned in to be something that inspired me to ask a question. The question I wanted to know is, what was up with the bubbles in the cake? How did the ingredients come together to bake little bubbles into batter? The ingredient that I pinned down as being the most interesting ended up being the baking powder. Up next, you can see why I was curious all about bubbles and some of the investigations I did about that ingredient, baking powder, to try and figure out more about how it influenced the texture and shape of anything that you bake. I was curious about how baking powder worked and wanted to do some kitchen chemistry with you to see if we can figure it out as a follow-up to our mug cupcake that we baked last time. I thought that if I tested some of the typical liquids that go into a baked recipe, like a cake or a muffin or a brownie, that I could figure out a little bit more about how baking powder works and what it looks like when it creates carbon dioxide gas bubbles. Let's take a look at a few tests to see what we can come up with. So first off, how do we know that baking powder is making carbon dioxide gas bubbles in our baked goods? Well, I took a look at the ingredients, and in this particular baking powder, there are two main active ingredients. With the powders that are in this jar, the monocalcium phosphate, the sodium bicarbonate, and the cornstarch, that somehow the liquid allows these two items to react and produce the carbon dioxide gas. I wonder why there would be different liquids needed in different recipes, so I'm going to take a look at how this baking powder reacts with a few common ingredients such as vinegar, milk, and oil, and then of course plain old water. So I'm going to compare each of those ingredients and show you what the reactions look like up close. Today I'm going to use half a teaspoon because I found that many of the small recipes I was making called for that exact amount. So just in case the amount matters, I'm going to stick with that. It also seems like a reasonable amount to use given how much baking powder I have left over here. So I'm going to go ahead and put a scoop, half teaspoon, into each of these test containers. So here's what the inside of one of our test cups looks like. Let's go ahead and see what happens when we start off with just some plain water. Right over here, this activity looks like some bubbles are coming up to the surface and they're mixing the solution around. It was interesting to me that the baking powder made bubbles with just the plain room temperature water, and now I'm curious to find out what happens when we use some warm water. So here is the warm water that I have. One idea that I have is that maybe this will make the chemical reaction happen faster. Sometimes heat can speed up a chemical reaction, and other times it can stop it from happening altogether. So I'm curious to find out if this will have a positive or negative effect on the speed and amount of carbon dioxide gas that the baking powder produces. Let's go ahead and pour it in and take a look. That was definitely a faster fizz. And look how much bigger these bubbles are compared to the ones we got in the first try. And I'm interested by these circles of carbon dioxide gas that are forming bubbles as they rise to the top. I planned my experiment to go in the order of what would be easiest to clean off of my measuring spoon. So that's the reason why I started with water. And next I'm going to go to what's the most similar, and that is the apple cider vinegar. So I'm going to pour some apple cider vinegar in my half tablespoon. And let's see what happens. Do you see anything different in the patterns of these bubbles? I saw a bunch of big bubbles form, some medium bubbles, and then in the middle, all of this effervescence is teeny tiny bubbles happening throughout the solution. This one reminds me of popcorn popping, where the kernels slow down as you get closer to getting more and more of them popped in the bag. I wonder why some of these bubbles are sticking together and others are going straight towards the edge of the container. Do you see that? Where the bubble pops up, if it's somewhere along the edge here, it immediately gets drawn to the side of the cupcake liner. So it looks like sometimes if the bubbles form too far away from the edge, that they pop. But if they form close to the edge like that one, that they're drawn all the way to the side before they pop. We're almost at our last segment of this experiment, and the next liquid I'm going to add to our baking powder is a half tablespoon of soy milk. Do you see that blob rising up? I wonder what that is. So it looks like there is something rising up here. I'm not sure if it's a mixture of the baking powder or the fat from the milk, but there's a foam that's rising, and as you can see, it's closing in on that last little bit that doesn't have foam. And then look, here's some bigger bubbles forming in the foam. So we have lots of teeny tiny foamy bubbles covering evenly across the surface, and then it looks like here and here and maybe right here, some bigger bubbles are starting to form. This one looks the most interesting. and hard to explain so far. Well, the last liquid we're going to add today to our baking powder experiment is some oil. Today I have vegetable oil, more specifically corn oil, which I know isn't the most typical thing that you would add to a cake or brownie, but it's either that or olive oil, which I have here. So we have this right over here. It's the thickest liquid that we're adding in. I wonder if it will also be similar to if I were adding the white of an egg, which a lot of recipes also call for in their liquid ingredients. Let's pour this on in and try to notice what changes. In this corner, I'm watching as the oil soaks into the baking powder bit by bit. I'm starting to notice some bubble-shaped spots in our solution, like there's one over here, and then several all along this way. I wonder if those will form air bubbles of carbon dioxide, or if they're just a coincidence in how the solution is mixing together. Oh no, I'm definitely convinced it does look like here, and here, and here, those are gas bubbles. Why do you think these bubbles might be behaving differently than our other experiments? My idea is that because the oil was so thick that the viscosity, the thickness, and the unwillingness to flow of that oil compared to the other thinner liquids is somehow holding the gas in the solution from all of these bubbles and is keeping them from getting to the surface. I wonder how long that will last, and if it's something that the bubbles can ever get big enough to overcome and pop at the surface, or if they're going to stay embedded in the solution. Oh, there's one. So it looks like this one just got loose and it's sticking to the side. I wonder how long it will stay, or if it'll pop. So I wasn't quite sure how long each of the reactions would last, but I left each experimental cup for a total of 15 minutes just to make sure no additional changes happened. And I want to show you what the final results were and some interesting patterns that unexpectedly formed in each of the experimental cups. Alright, first one up, this was with the room temperature water. And the pattern I was talking about is I noticed that when I tip most of these cups, there's a little pattern of bubbles left at the bottom from where the gas passed to the undissolved baking powder. So that one was our plain water. Our warm water from our tea kettle looks like this. I noticed that it almost looks like a little footprint of the bubble pattern that formed. Remember that this one went much faster and fizzier than the room temperature water. This one looks really interesting. Here's from the apple cider vinegar, and these were the indents left behind from the gas bubbles coming out of the baking powder and vinegar solution. Some big, medium, and really small. Remember, this was the one that had a variety of bubbles and was almost effervescent in how they were sprinkled throughout. It reminded me of an Alka-Seltzer tablet that we used for our rocket experiments. Alright, with our soy milk over here, the foam that was on there is kind of turned a little bit clumpy, and a lot of those bubbles have popped. And if you look on the bottom, there's still a little bit of that foam clinging to the side and some more bubbles on the bottom. And finally, our vegetable oil experiment, where we had a few very slow moving bubbles, and it looks like everything in here kind of looks the same, but without all of the bubbles in it that were there before. This little bit of baking powder over here never really dissolved into the solution, so I'm interested to know why that didn't happen and why that part right there isn't getting wet by the oil or engulfed into the solution at all, even though the rest of them, without stirring, definitely had some amount of getting combined. Alright friends, so I did a little bit more research about baking powder after exploring all of the reactions with the different liquids and how it bubbled. What I learned was that this baking powder is called double acting. That means that by having the two powders mixed together, both a weak acid and a weak base, that they're able to actually continue creating carbon dioxide gas, first when they're mixed into the liquid of the batter of your recipe, and secondly throughout the cooking process to keep your item soft, springy, and able to rise like our cake did in the video. Another thing that I thought about after making all of those different bubbles with the different liquids using baking powder is, well, how lucky we are to have this little bit of chemistry in our delicious desserts. Because after all, if you were to use something like baking soda, you would have to add vinegar. And I don't know about you, but this doesn't look like as much of a delicious cake as what we were able to create in our experiment. At CuriOdyssey, we like to say that doing chemistry is as close as you'll ever get to being a real-life magician. So if you liked this experiment with kitchen chemistry, exploring acids and bases through baking powder, and you want to know more about how to do things like this, check out our CuriOdyssey at-home science activities. I hope you do try some of these at home.